All right, let's hope this works. I'm gonna try to one-shot this. There might have to be some edits or whatever if it looks like it's going on too long or if I get tripped up on myself trying to explain how all this works, but we'll try to one-shot this. So we have the Rush project. We have it in the ex00 directory as usual, and these are our files. Rush1 isn't there. That was just for me testing it earlier. Okay, so where to start? I guess the best thing to do is to start in the main. So let's open up the main. We have a couple of helper functions here, which are pretty straightforward. The put character function, as usual, we're just writing a single character to the standard output. Put number is the same thing as put character. We're just putting a number character out, and we're just using our put character here. Print board is the first one that's kind of relevant to our project today. Here we're passing in the board, which is a 4x4 square. That says the first part of the problem required us to do is a 4x4. It doesn't have any kind of return. All right, I'm not going to go through line by line and explain everything. If there's questions after you've watched the video, let me know and we can address those in particular, but I just kind of want to give you an overall idea of what's happening in the flow of the program. I know there might be a language barrier issue in this explanation as well, so I'm trying to go slowly, not to be like an idiot, but it's just because I know somebody might be translating this for somebody else. On Monday, if there's still issues, we can take all day Monday to grasp this, so no worries there. Okay, that being said, so print board, this is just how we show the board to the user in the CLI once it's complete. The only thing really to know here is that we're passing in the board, which is a two-dimensional array. These would be like everything in a row and then every position in that row. And then while the I is less than 4, because there's a 0 index for arrays, so this will count 4 times, but starting from 0. This is going to loop through the second part of the array here, so it's just a double stacked while loop. Personally, a for loop would be easier here, but okay, that's norm. And then we're going to put the number that's stored in the jth element of the ith dimension of the array. So let's say this is 0, so on the 0th dimension, we'll put the 0th number. Then we'll loop through it again, and we'll put the 0th row, the first number, loop through it again, 0th row, second number, loop through it again, 0th row, third number. Well, now j is not less than 4, it is equal to 4. So we're going to come out here, put a new line so that we can start printing the next row, increment I by 1, boop, 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 we come back here up, I is now 1, 1 is less than 4. We set j to 0, so now we're on the first row, or the first row of these, and starting to print the 0th character, which is the first character of the row. So that's how print board works. I removed put this new line here just because, as you noted, it didn't match the output in the PDF. So just to be careful, I removed the final new line after we printed out a board. It would be a shame to miss out on this project because of that. The next thing that is maybe going to be new is the void pointer return here in FTB0. FTB0 is just a way to set all of the things in an initial board to 0. So when we make a new board, the 4x4 set of squares, they're not set to anything by default. So we use B0 to set all of those to 0. And also if we need to rework a board, it also resets them to 0. The only thing here maybe is the void pointer. That just means that you can kind of use it generically. So, I mean, you could set characters to 0, an array of characters to 0. You could set an array of integers to 0. You could set an array of a custom type to 0. That's like the best thing to get for a void pointer is that it lets you kind of work in generic ways with C. I don't think you'll need void pointers until like, if I remember, it's like C11 when the linked lists start. So don't stress too much. But just in case they ask on the exam, the reason we used a void pointer here is just so this is a generic method. We could change these as well to be integers because that's all we're working with, but it just makes it a little bit easier. And again, this loops through every part of the one-dimensional. We're just passing in here the views, right? The views here. Where do we use the B0 at? Yeah, here. So we're passing in the board here, and then we're saying, okay, so we're going to do this, right? This is the number of things that we're doing for. We're going to do it for 4 times 4 times, so 16 times the size of an integer. So if the system perhaps had a different size for an integer, this would account for that. That's really the only thing here that might be a little rough for now. And if it is, we can always rewrite this. We can do it a different way with nested while loops. But this just is, I guess it's good if you can grasp this, the void pointers now, because it's going to carry you through C until the end. So that's B0. Those are all of the helper functions that we're going to use in here in our main. In our main, we are receiving, I'm not sure if you've gotten to command line arguments yet. If not, I'll just quickly explain them. For a command line argument, this allows us to pass arguments to the program from the command line. So like the subject said to us, that the user is going to give us a string of 16 characters, each representing a different clue point for the grid that we're trying to solve. So what's going to happen there is that this should be 1, right? Because we're going to get the name of the program, which is the 0th element, and then we're going to get the string that they're passing to us, which will be the first. So that's why we're checking here. If argc does not equal 2, okay? If we're not equaling 2, or if when we parse the input, which will go into that, it's not a valid input, we're going to write an error, and then we're going to return 1. This means that we don't have a valid number of arguments. We either have too few or we have too many. And the input that they gave us is not valid. We'll step into that next, the parse input. So that's just a check for errors here to make sure that we're not trying to waste time parsing boards that are invalid, or if they don't give us enough inputs. So then we set the board to 0. This is that B0 is explaining. We set the board to 0, so every position is now 0. We haven't solved anything yet. 0 is not one of the valid characters, so 0 is a good thing to hold it with. And then we do, if the board is not solved, we're going to write error. That means the board is not solvable. Solve is recursive, so I'll explain that in a second as well. I just want to walk through it step by step. So we'll do parse input first, and then we'll move to the solver. But just so you know, here we're setting the starting position, which is the upper left corner. So if you think of it as a grid, you have 0, 1, 0, 2, 0, 3, 0, 4, 1, 1, 1, 2, 1, 3, 1, 4, 2, 1, 2, 2, 2, 3, 2, 4, and so on. This is just saying start this recursive solving process. At the top left element, we're passing in the board, and then we're passing in the views. The views are what we're going to take from parse input, and the views are going to be the array of characters that the user has given us from the command line. So views might seem confusing. Maybe I should have used clues for that instead. Those are the clues. So views are clues, the board is the board, if that helps, because you'll see views and clues or views and board throughout the whole program. That's just us passing around the board and views so we can use it within the program. So again, if the board is not solvable, so this will finally return once it's tried all of the possible solutions. That's the recursion happening, right? So if it tries all the possible solutions, it doesn't find a solution, then we know we have a string that doesn't have a solution, and we're supposed to write error there. 1 here is for the standard output. Error here is to let them know that it's an error, and then 6 is the count of characters inside of error, in case we're still a little confused with right. Otherwise, we're going to print the board. So this uses the print board method from above. We pass it the board, it prints out the board, and we present them with our solution. That is the flow of main. Let me have some coffee real quick. Pretty straightforward. There's not a lot going on in main. Let's dig into parse input. Actually, we'll do parse input last. Just assume that this is going to tell you if it's valid or invalid. I don't want to break the flow of working through the program to do something small like look at the parser. So after we've done this, the major thing that we're going to do next, it's a good tip as well if you're trying to read code that's already been developed, drop into the main, see what's going on, and then just trace the program as it walks through the different methods or functions that they might be running through. So here we see that we're doing a solve. Okay, so let's figure out what solve does. Okay, so here is our solver file. We are having the use of here of isValidPlacement. We're having check views, and we're having check views partial. I'll explain what these mean as we go. These are just like some helper functions that are stored in another file that we need for this one. But I was just trying to keep the files nice, small, and modular so it's easy to explain, and we can pause the video, go back, whatever, on Monday, figure it out together. So solve returns an integer, which is going to be a true or false value, so 1 or 0. It takes into it the row that we're currently checking, the column that we're currently checking, the board in its current state, and the views or the clues. This is important because it's recursive. So recursive means a function that calls itself from within itself, right? So every time that it calls itself, it's going to put a new call of itself on the stack. The stack is just kind of like, think like a local memory storage. I'm not explaining it in a depth because I don't think we have to have stack and heap down just yet at this point, but just know that the stack is like a local place of memory that all of the calls that your function makes, or that your program makes, so when it calls different functions, it places them on the stack, and then it resolves them, right? It resolves them from like the order that they're put in there. It resolves them in the reverse order. So if something's put in there first, and then something goes on top of it, and on top of it, on top of it, it's going to start going from the top down, 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 down to your original one. So that's helpful to know for recursion. When you're calling a method inside of itself, it hasn't completed itself yet, right? So it's just going to add another call of itself on top, another call of itself on top, another call of itself on top until it gets to an end condition. When it gets the end condition, then it'll finally process all of those things back until it gets to the first call, and then it makes its return. I hope that made some sense. My microphone is glitching a little bit. I hope that made some sense. If not, we can try to go over some recursion with like visual diagrams on Monday. It might be easier to visualize it. I'll bring my iPad and then we can do some drawings and stuff. But mostly the best thing to know is that recursion means that a function is calling itself. So it might be a bit hard to wrap your brain around. I know it took me years to get recursion. If you've got it, that's awesome. But okay, that being said, let's now step into the function. So in here, we're checking if we are on the fourth element of the row, right? So we're passing in row here. As this continues to call itself, it's going to be incrementing the row and the column. That's how we're solving the board, right? So if we are on the fourth row, then we know that the board is complete, right? We are on the fourth row. There's nowhere else to go. There's no more rows that we could have to solve. So we are going to do check views. Check views checks the whole board. It checks all of the clues, and it checks to see if the clues match how we actually have the line oriented. I'll show that to you when we get into check views. So just know that when we have if row is equal to 4, we're checking if the board is solved. Check views is more or less check board is solved. If the column is equal to 4, right? So that means we are now on the fourth column of a row. We are going to return solve plus row plus 1, and then we're on the 0th column. So this is the recursion, right? So we've made it to the end of the column, and we haven't had any issues with the valid placement of numbers, so we can assume that that column is solved, at least until we have to backtrack. So we can assume that the column is solved. So we call solve again. This is that recursion. But now we are going to increase the row by 1. So we're moving to the first row, or the second row, or the third row, and if we hit the fourth row, that means we solved it, so we'd be here. And we're going to set the column back to 0, so we're starting now at the next row, the leftist point, and then trying to build the board from there. Again, we're passing in the board, and then these are the clues. So here we go through while the number is less than or equal to 4, because our clues say we can have numbers 1 through 4. That's why we're setting number here to 1 and not 0. We're going to check if the number is a valid placement based on the row, column, the number itself, and the board. We'll go into isValidPlacement next. Just assume that for now, to understand the rest of this, isValidPlacement says, does this number break any of the rules? Meaning, is this number present already in the column that we're in? So it looks up and down and says, okay, I'm a 4. Are there any other 4s in this column? If not, okay. Are there any other 4s in this row? If not, okay. And that's from left to right. And then we look from right to left. Are there any other 4s in this row from right to left? And then whatever position we have in the right column, we go, okay, is there any, let's say, 1s in this column, top to bottom? So that's how we're checking our clues for the boards. And there's also a check for the bottom, but I think you've got the idea. So then we go ahead and we set the board row and column. So let's say we're in the first row, column 3. We're going to set that to whatever number is here, right? The number that we're iterating through here. And now we're going to run check views partial. This is similar to check views, which checks the whole board. Check views partial is just an optimization that I added to make sure that if we have an invalid row or an invalid column, we don't continue to recurse through the whole process and only come to that conclusion at the end. We exit early, we reset the board, and we start checking the next set of solutions. So here we check the views partial. It takes the same stuff as we do for check views, except we also have to give it a row and column because it has to know where it's currently at in its partial check. And if the solve row plus column plus 1 plus boards plus views, we return 1. So this is where we're saying we have solved the puzzle. So if the check views partial is good, and if the solver for the next column, right? So we've now said where we're at is good. So now we're going to recursively call solve from here. And from here, we're going to be checking the next column, the next column, the next column, the next column, and checking to make sure that everything is good. If it's good, we're going to be returning 1. We have solved the puzzle. If not, this is where the backtracking comes in, right? So then as that stack starts to resolve where it says, no, we didn't solve the puzzle, it's going to set the row and column that we sent to it to 0. So we tried 4 numbers. We found out, oh, those 4 numbers don't work. So now we need to roll back those. So we roll back, set the 4th position to 0, roll back, set the 3rd position to 0, roll back, set the 2nd position to 0, roll back, set the 1st position to 0. That's the backtracking. That's really the hardest part of this exercise, was to do recursive backtracking. If we get any questions about that on the test, if you feel confident for it, go for it. If not, I'll try to see if I can direct them to me. But if you get that, you're going to be good for honestly everything in the curriculum, even up to maybe the binary tree searches and stuff. So really take the time to try to get what's happening there. I will make diagrams for Monday to kind of explain the stack and recursion, because if you get that, that's super huge. I mean, it's quite possible you already do. I don't know where your guys' levels are, so I'm just kind of shooting at the wind and assuming that we don't have anything, just to cover all of our bases. But perhaps you already have it, and if you do, that's amazing. You're well ahead of where you're supposed to be. So yeah, what's happening here is that we're putting them onto the stack, and then we're checking to see if that's a good solution. If not, then we roll it back one by one, set the board back to 0, and then down here we increase the number and we try another number. So all of this was saying, we're going to try number 1. We're going to put number 1 into the board. We're going to check if that view works with number 1 in that board. And if it also works in another position. If it doesn't work at all, we're going to say, okay, we are going to reset the board and we're going to try the second number. So this is our brute force, just kind of trying all the different numbers in a row and column placement until we find all of them that work and the board is solved. This can roll back once, this can roll back twice, this can roll back 3 times. It really depends on how far we tried until we found one that didn't work. Okay, so that's the majority of the hard part of the program. Everything else is parsing and checking rows. So this is the heart of the program. The solver is the heart of our program. If they ask what solver does, solver is a recursive method that progressively checks each potential number against its position in the board relative to the other numbers that have already been solved. That's the best way to explain the solver method. So what do we use in solver method? We use check views, we use is valid placements, and we check views partial. So let's go look at those right now, right? So let's go check the views. Let's start with check views. And if you can see, we're already through most of the files here. They're not too bad. Okay, this uses some helper functions. Count visible row left, count visible row right, count visible column top, count visible column bottom. Those all take columns and or rows respective to their column or row designation, and then the board that is a 4x4. These are in another file. We'll look at these. These are even less complicated versions of what we have to do, but we use them here, so it's important to note that they're there. So in our check views, remember check views, I should have actually put it as like validate square, but it's where we check if we're standing in one position, if we can see all of the towers. That's why it's called check views, because this is more or less a Sudoku puzzle with height elements, right? So in Sudoku, you have to have only one of each number on each column and row. However, this adds also that numbers have different heights and can block the view of other numbers behind them. So that's why I went with check views instead of check square. I hope that makes sense. So check views takes the board in its current state, and then it takes the views, which are the clues. Here we are going to walk through it and say, while I is less than 4, right, because there's the possibility of 4 columns or 4 rows, we're going to say if the count visible column top 1 for this number that we're checking here, and the board does not equal the views in that position, so views 0 has a clue, and we're checking here, well, this clue says 4. From the column top position of I, can we see all of the other numbers that we're supposed to be able to see? Can we see all of the other buildings or skyscrapers that we're supposed to be able to see? If not, we return 0, and that means that this was not a valid square, and so we just don't have to do the extra counts. That's the only reason that we're returning here, instead of like storing it in some kind of a value. If it fails at any one of these points, that means we don't have a valid board. This is the same thing for the bottom of the board, right? So it's the same exact view here. These will make more sense when we go into the count visible column. These are in the view utilities. We do the same thing from the bottom. We're checking the position versus the views that we should expect, right? So this means that we are on view position 4 plus I. That's taking into account that it's a 16-digit array of integers, and we're moving ourselves to the 4th plus I position of the views. So the way that they're input here, I believe it was like, let me say, okay, yeah, so it's column top 2, column top 3, column top 4, and then that's why it's plus 4. So we've moved through all the 4. The next input is the bottom. So for checking the bottom, we have to move through the first 4 and then move to the 4th element plus I. Since this will be set to 0 or 1 while we're doing this, we'll know that we are in the position of checking the column bottom 1, column bottom 2, column bottom 3. Same thing here. That's why we have the 8 here. To get to the row lefts, we have to move 8 characters in, and then to get to the row rights, we have to move 12 characters in. That's where these numbers come from. So if they ask us these, that's where they come from. I guess I could have put like a define for, bottom offset, left offset, right offset. But just get that these are moving through the array of integers that we have here by this many, and then counting where we're at here. Okay, so these do the exact same thing on the left. These do the exact same thing on the right. So we're checking like this, right? We're checking, does it work like this way? We're checking, does it work like this way? So from top to bottom, then we're checking bottom to top, moving over top to bottom to top, moving over bottom, 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 bottom. Okay, now we've done those. That's these two. Now we're checking row left, row left, row left, row left, row right, row right, row right, row right. Okay, so we're just checking the clues on the side versus what the actual row is. I hope that makes some sense. To summarize this file, this is our solution checker to make sure that our completed board is correct. We check systematically the columns from the top to the bottom, then we check from the bottom to the top, then we check from the left to the right, and then from the right to the left. So this is our column checker. And if you remember, if we go into solver, that was used here. So when we are at the final row, we are checking the board to see if it's solved. The other one is check views partial. So let's go look at check views partial. Okay, check views partial is almost identical to check views, except we don't have to do as many views checks, I guess. Okay, so again, we have the count visible because we have to use those. These are the exact same methods that our other one used, that our check views used. So once we look at these, you'll be familiar with them in both files. We have two methods in here, check row, which is just checking an individual row. It takes the board and all of the clues. We're going to check if the board is filled, and while it's filled board, we're going to see if, while we are, checking an actual valid position on the board, if board row I++ is equal to 0, the filled is equal to 0. So we're checking, okay, is this row a filled row? Is there something in this row or not? And if not, okay, we're saying, okay, this is not filled. It's an empty space in the row. If the position is filled, right, we want to actually check if that makes sense relative to where we're at. So here we're checking if the view from the left is correct by sending in the row that we're currently checking, the board that we're currently checking, and we're seeing if it is not equal to what we're expected in the clue. If it's not what we expect in the clue, we're returning 0. That means the row is not good. Then we check the row also from the right. If that also doesn't return the value that we expect from the clue, we return 0, meaning also that the row is not solved. So that could be either we have a mistake in the row solving, but more likely than not, it just means that the row itself isn't complete. Columns is the exact same logic, except we're going from top to bottom and then bottom to top. So if you got this, you'll have this. If it's not solved, if it's blank, if it's wrong, we're returning 0s. Otherwise, we return 1 to let it know that it's a checked column, valid column, and that it's a checked row, valid row. Here's where the actual views check partial is. This should look really similar to our other one of check views. This checks the row, right, to see if it's valid. And then this checks the column to see if it's valid. And then if it is, we return 1. This is really just an optimization. We could wait and check the entire board at the end. But if you think about it, if we wait until the end, we have to now backtrack all the way through all of those numbers that were incorrect, set them back to 0, and restart again. It's going to increase the time of execution for the program quite a bit for mistakes that we make later in the execution of the program. So it's best to just check them partially as we go. So the best thing if they ask us, why did we use this versus the check views? This is an optimization to ensure that we're not continuing to populate our grid with numbers once we've made an incorrect number placement. So it's just an optimization. Okay, there's not much left to go over here. Let's go ahead and look at the visibility utilities because we've seen a lot of those. Oh, not BIM, visibility utilities. So once you get one of these, you'll get all of them. The only difference is like here we're setting I to a different value, but because we're checking from a different position on the grid. So we're counting visible row left. So the reason it's called counting is because the clue is telling us how many things should be visible from that side. And to count it to be visible means that it is a lesser number than the number we're checking from, if that makes sense. So if we have a 1 as a clue, that means that we should be able to see only one thing, which means that we should have a 4 there because 4 will block everything. If we have a 2 in the column as a clue, that means that we'll see building 3, we'll see building 4, and then we'll stop because 3 can still be seen. It doesn't block 4, it's shorter than 4. If we have a 3, that means that we should have a 2 in the first place, a 3 in the second place, a 4 in the fourth place, and then a 1 in the fifth place by logical deduction because the 2 says, okay, or the 3 says we should be able to see over building 2, over building 3, can't see over building 4, 1 must be behind it. And then if we see a 4, then we know they should be in an order of 1, 2, 3, 4. With that, what we're doing here is more or less here saying, okay, well, this number is less than 4. So while we're still checking from the left position and working our way over to the right, we're putting the value that's in the board row I here. We're checking if the value is greater than the max, okay? The max is going to be what we expect that we should be able to see based on the clue. So if the value is 0, right, and max is also 0, it's not going to be greater than it. So we're going to increase the I here. We're going to check the position here as well. So we're just checking that as long as this is greater than this is going to get set to this, and we move forward. So we're just saying, okay, we're at this position. This is how many we should see. Does that work? Yeah. Okay, let's move and check the next position. That's why we're increasing it there. Does it work here? Yeah, okay, let's move and increase the next position. But now, if value is smaller than the maximum, which we know is going to be the 4 for that row, because that's increasing each time we move through it, we can say, okay, this is probably not a correct row. We're going to return how many we found before this became imbalanced. So as we've stepped through it, let's say we have a 4 in the middle in position 3. Okay, 1, okay, 2, okay. Oh, we hit the 4. Okay, so that means we've only gotten to see 3 there, so let's return count. Does the count of 3 match the clue? If it does, great, we solved the line. If not, no, that means we need to backtrack. I hope that made sense. This might also be easier to explain with a visual diagram. And then these are the only tricky part in here is when we set this to 3. That's because we're starting from the right, right? So then we need to go from the right and subtract our position down. That's why we have the I minus minus here versus the I plus plus. Right to left, right. So left to right plus plus. Right to left minus minus. The same thing with the columns from the top to the bottom. The I's, there's a difference, and the 3's are here. Other than that, it's the exact same logic, as you can see here. The exact same logic. So that's how we're checking whether or not a row or a column is valid. If those were a sticking point, let me know. It could have just been that I didn't explain them well enough. So yeah, okay. And the video is getting long, so I'm just trying to keep you from having to spend your whole Sunday afternoon watching me ramble about programming. The only other things we have to check is valid placement and parse input. So is valid placement. This is really just checking to see if in that column or if in that row there is already that number. So here we're passing in the row, we're passing in the column, we're passing in the number, and then the board itself. We're saying while I is less than 4, right? So while there's still something to check, if that board's row, our number that we're checking, right, is equal to that row's current position, right? So row 0, row 1, row 2, row 3, okay, then row 2, row 1, row 2, row 3. That's why we're passing in the row here, because we're only checking one row, we're only checking one column, because each number can only interact with 2 of those at any given time. So if that position that we're currently checking is equal to number, or the column that we're checking is equal to number, we're returning 0. It's not a valid placement. There can't be duplicate numbers. This is like where the Sudoku logic comes in. There can't be a duplicate number in a column or a row. So here we're just checking to see if that number already exists. If it does, we're going to return 0. Otherwise, we increase I and we check for the next number or the next position. And then if it's not, then we return 1. We know it's a valid placement and we can move forward. Where does this come into play? So in Solver, here, we're checking if the current number, right? Remember we were working through numbers 1 through 4 to see if we can place them in the grid. If that number is a valid placement, that's where we go ahead and add it to the board. And then, now we know how the check views partial works, we check if that number that we just placed in the board works, and if we can continue to solve the puzzle. So we're assuming that this is correct. We're walking through and continuing to solve the puzzle. Oh, we found a place where it doesn't. This is going to return false. And we're going to reset that position back to 0 all the way down until we're resetting this also back to 0. And then this increases. We set that to the next number and we repeat the process. That's really how this program works. And valid placement is just checking to make sure there's no duplicate numbers. So I hope that helps make some sense. We have one last to check, I think was parse input. Yeah. Okay, so this method is quite simple. We're just checking the views that they gave us, right? The clues, the views are the clues. So we're just checking that the views that they gave us are actually what we should expect as far as a valid view, right? So like the numbers and stuff they gave us in the PDF. I don't know if I can pull it up on my computer. No, I can't. But what we're doing is pretty much making sure that they're good sets of 4x4s, right? So here's where we're setting our counters. These are double while loop. It's just customary to use I and J when you're doing while loops. Honestly, we use them in for loops, but because of norm, we're not allowed to use for loops. Sorry, I just want to have some coffee before it's cold. So here we're saying while the argument, right, I. So while there are arguments to go through and check, if the argument I is greater than or equal to 1, and the argument I is less than or equal to 4, it's letting us know, okay, those are numbers that we expect to have given to us. They're not 20s or 30s or -5s or whatever. They need to have numbers of 1 through 4 for our current puzzle. If we were to try a bonus, which would make this a bit harder, but we could adjust it. Let's not though. These would be a different range. This would be like 1 through 9 if we were doing like a true Sudoku 9x9 puzzle. So this is just checking your range, making sure the number is valid inside of your range. And then this is checking that the j here is greater than or equal to 16, right? So if j, because this is a 0 indexed array, right? So 16 is too many, we would need to have 15. So if the number is valid, and if the array is 16 or less characters, or 16 or more characters, excuse me, we're going to return 0. It's not valid because we can only have 16 characters of our input that they're giving us. And then we're going to increase I by 1. And now we're checking, does the argument in the I position, is it blank? So is there nothing there? Is it invalid, or is it the end of the string? If it is, we're also going to return 0 because that's an invalid string. That's only if, right here, this is like the number ourself here, into the views, does not equal a valid number, right? We're checking, okay, is it a space or something? And if it's not a space, right, or it's not the end of line, then it's invalid as well, just because it's an invalid white space character. So here we're checking for valid numbers, here we're checking for invalid white space characters. Now we're checking if it is a valid white space character. So if it's not one of the numbers, but it's not an invalidly placed character, right? Then we're checking, is it a space character? Because these are space separated lists. If it is, okay, we increase, and we're checking the next number in the views array here, right? We're tracking this with the argument position here and the view position here. And then we return 0 if it's not good, and if it is good, we're going to return the final check that there are only 16. So this will return true if it's true, if there's 16, false if it's false. And that's our parser for making sure that the input string is correct. Again, if this is a bit much, this might be better explained through like a visual diagram, but honestly, I think you two have got this, and if not, no worries. Okay, so how do we use this? Well, let's try one of the solutions they gave us. First, let's try an improper solution. So let's compile it. And let's put it to rush01 as an output. And then we need to include all of the C files in the current directory. Okay. Now, when we just run this without any input, because it's an invalid string, right? But that's the first check. That's checking, are there the correct number of arguments? No, so there's an error. Now let's try a random set of 16 numbers. The likelihood of this passing is very low. Let me make sure I got them right. So 1, 3, 4, 2, 4, 3, 2, 1. And then another one would be, let's see, 2, 1, 4, 3. And then let's do 3, 4, 2, 1. Okay. So that is not a solvable puzzle. Let's take one that is a solvable puzzle. Error is what we should expect for an unsolvable puzzle. All right, let's take this puzzle here, which they said does have a solution in the exercise. And we see there, we have the solution puzzle. They want us to run it with the cat E just so we can check new lines. And there we go, that's the output as expected from the program. I'm going to make a change right now because I don't want to forget to do this when we submit the project, and that's remove the new line character. Not in this one, it's in solver. Nope, it's in main. I have my stuff spread all over the place, you guys. Okay, print board, we don't need this here. Okay, so there we go. That's the project. I hope that made some sense. I hope it was at least straightforward enough. If you have other questions, feel free to ask me, send me a message. Let me just do this so I don't forget. Fixed new line character. Okay, so the new one is up there on the GitHub. If you want to download it, you can do so. I'll send you the message on Slack. If you have any questions, feel free to ask. I know this is a long video. This is a big project to explain. If you can get the parsing down, if you can get the checking the valid rows, if you can get checking the board down, that's great. If you can learn something from it, that's great too. We have all day Monday. Luckily, they've moved our evaluations from Tuesday till Monday, so we have all day Monday to spend on this. I'll be there on campus on Monday, and I'm available 100% of the time through that day. I don't care if it takes us all day to walk through this. We'll do it. So ping me on Monday when you guys are ready, and we'll talk through this together. We've got this. We've got a working rush. Now it's just a matter of being able to explain it, and we should be able to pass this rush. Let's hope with 100%. All right, you guys, take care. Have nice weekends. Sorry this was a 40-minute video. Bye-bye.